In the previous lecture on a specific heat of solid, you have seen the classical theory of a specific heat of solid. Or in other words, you can say we have seen actually the Dulong-Petit's law. And you have seen that according to classical theory of a specific heat capacity of solid, the specific heat capacity of any solid is equal to 3R, as I have mentioned it here, you can see. And so this result shows that a specific heat of solid is independent of temperature. But in that lecture, we have compared this theoretical result with the experimental observation, and you know, experimentally it is observed that the specific heat of solid depends strongly on temperature, particularly at low temperature, although at higher temperature this classical result agrees with the experimental result, because experiment also says that a specific heat of solid is independent of temperature, but only when temperature is very high. But in low temperature region, the specific heat of solid decreases with decrease in temperature. And finally, at 0 Kelvin temperature, you have seen the specific heat of solid becomes 0. But this result, which is known as Dulong-Petit's law, that is Cv equal to 3R, does not agree with this experimental fact. So actually, as an attempt to explain the variation of a specific heat with temperature, Einstein in 1907, on the basis of quantum theory, proposed a new model or new theory for a specific heat of solid. In fact, in the derivation of this formula for a specific heat by Einstein, he utilized the quantum theory, and you know basically that quantum theory was proposed by Max Planck. So considering the idea underlined by Max Planck, Einstein developed the theory of a specific heat for solids. And you know, according to this quantum theory, the energy of oscillating system varies not in a continuous manner, but in discrete manner. Actually, energy is absorbed or energy is emitted in a definite packet or quanta, in fact, which is an integral multiple of an elementary quantum of energy that is called h nu. You have studied this, that energy emitted by an oscillator is an integral multiple of a quantum of energy which is denoted by h nu, and where this h is Planck's constant and nu is actually the frequency of oscillation. In fact, during the derivation of formula for black body radiation, Max Planck has derived the average energy of a vibrating oscillator. In fact, Einstein utilized that formula to get the expression for a specific heat of solid. And what actually he assumed and what actually differentiate Einstein's theory from classical theory. Let us see these things just as an assumption of Einstein's theory. So Einstein's theory, which aim is actually to deal with the temperature dependence of the specific heat of solid. To develop this theory, Einstein made some of the important assumptions. So first of all, we will see what are the assumptions on which Einstein's theory of a specific heat is based. First of all, let us see this. In fact, this theory is basically based on the following assumptions, which I have mentioned it here for your convenience. And according to these assumptions, first one is the atoms in a solid are all independent and that each atom acts as a simple harmonic oscillator vibrating with a common frequency nu. It means the frequency of vibration of any atom is not affected by the presence of the uh, other atoms. Although you know solid is a dense material where the atoms are closely packed, but even after that, Einstein assumed that the vibration of a particular atom is completely independent of the presence or of the vibration of the neighboring atoms. So you may say that Einstein considered a monochromatic vibration of the atoms, or in other words you can say the atomic vibrations is characterized by one and the same frequency as assumed by Einstein. So this is the first assumption, although when we will discuss the device theory then you will see that this assumption is actually faulty. In fact, the frequency of vibration of an atom will be affected, will depend on the frequency of vibration of the neighboring atoms. But when you discuss Einstein's theory, you have to say that the frequency of vibration of an atom is fixed, of all atoms are same, and that particular frequency is independent of the vibration of neighboring atoms. So this is the first assumption of Einstein's theory. In second assumption you can say that each atom of a solid has 3 degrees of freedom, and you know the molecules of a perfect monatomic gas has 3 degrees of freedom. So Einstein assumed that like the molecule of a monochromatic gas, every atom of a solid has actually 3 degrees of freedom. So degree of freedom, whenever will be needed, we will write it 3 for an atom according to the assumption of Einstein's theory. And as I have told you earlier, that Einstein actually used the formula derived by Max Planck while deriving the famous Planck's formula by Max Planck. The average energy of an oscillator will be what? As you have seen in the classical theory, it is assumed that the average energy per oscillator per degree of freedom is equal to kT. But Einstein does not utilize this formula, this classical theory, because this is a classical result. As I have told you earlier that Einstein's theory is based on quantum theory of Max Planck, and according to Planck's quantum theory, the average energy per oscillator per degree of freedom is given by this formula. This is epsilon bar equal to h nu divided by e to the power h nu by kT minus 1. So this formula was used by Einstein to find the expression for a specific heat of solid. I hope you know each and every term in this formula. Here actually h is Planck's constant, nu is frequency of vibration, and k is Boltzmann constant. You know it. Now, as you have seen in this assumption that Einstein assumed that the degree of freedom of an atom is equal to 3, and this expression actually gives the average energy per oscillator. Atom means here atom is treated like an oscillator. So you can also say this is average energy of one atom for 1 degree of freedom. But since the atom has 3 degree of freedom, so the total energy of each atom will be what? We will simply multiply this expression defined in equation 1 by the degree of freedom which is actually equal to 3. So you can see as the degree of freedom freedom of each atom F equal to 3. So the energy of each atom what will be the energy of each atom? If you denote this energy by the symbol E, this will be simply equal to F times average energy per atom per degree of freedom. And as you know, F is equal to 3, and see this equation 1, the average energy per atom per degree of freedom is what? This is h nu divided by e to the power h nu over kT minus 1. So this will be 3 h nu over e raised to the power h nu divided by kT minus 1. This is actually energy of each and every atom of the solid at temperature T. Now, if you consider 1 gram mole of your solid, then you know in 1 gram mole of a solid, the number of atoms is simply equal to Avogadro number. And since each atom has this much energy, so if you want to find the value of energy of 1 gram mole of the solid, what you will do? Actually, you should simply multiply the number of atoms, that is Avogadro number, to this value of energy. Then you will get actually the energy of 1 gram mole of the solid. Now, as number of atoms in 1 gram mole of a solid is equal to what? Is equal to Na. You know it. Where? What is this Na? Can you say? Where Na equal to Avogadro number. You know it. Avogadro's number. And so the energy of 1 gram mole of the solid at temperature T is, what will be that? We will simply multiply this value of energy E to this number of atoms, which is actually Avogadro number, because we are considering only 1 gram mole of the solid, and in 1 gram mole of the solid, the number of atoms will be simply equal to Avogadro number. And since each atom has this much energy, so the energy of Na atoms will be simply Na times this much. So if you denote this energy by the symbol U, so what will be that U? That U will be equal to Na times that much. So that will be 3 Na into h nu over e raised to the power h nu over kT minus 1. So in this way, Einstein obtained the value of energy of 1 gram mole of a solid at a temperature T by utilizing the formula for average energy per oscillator per degree of freedom proposed by Max Planck. Now, as you know the energy of 1 gram mole, you can now simply find what will be the specific heat capacity of the solid, because you know the definition of a specific heat capacity of solid is what? That will be simply the temperature derivative of this energy. So hence a specific heat of the solid. When you write Cv, that means at constant volume, at constant volume. Although it is not needed here in case of solid to specify that this is a specific heat at constant volume, because in case of solids we always define only the specific heat capacity at constant volume, because in this case there is no appreciable change in volume due to the change in temperature, so volume almost remains constant. So here a specific heat means a specific heat at constant volume. So there is no need to say that this is a specific heat at constant volume. You may simply call it a specific heat of solid. And you know, this Cv is defined as a del U by del T. Although here you can see U is only a function of T, so you may equivalently write it simply du by dt. There is no need to write this partial derivative. Now let us put the value of U from this equation 1 and differentiate it. You will simply get the expression for a specific heat of solid. So you can see this will be what? This is d dt, and put the value of U. See the equation 1. This is 3Na times h nu over e raised to the power h nu over kt minus 1. And as you know, this 3Na times h nu is independent of temperature. This is constant. So we will take it outside of the differential operator. So this is 3Na h nu over d dt. Now take the factor in denominator in numerator so that it will be easier to differentiate it. So this is e raised to the power h nu over kt minus 1 raised to the power minus 1. Now differentiate it. You can see this 3Na times h nu will remain same. Now we will differentiate this factor with respect to t. So you can see this is simply minus 1 times e raised to the power h nu over kt minus 1 raised to the power minus 2 times. Now we will differentiate this term e raised to the power h nu by kt with respect to t. So what will be this? This will be simply equal to e raised to the power h nu by kt times minus h nu divided by kt square. In fact, h nu by k will remain is a constant factor, and when you will differentiate 1 by t with respect to t, that will be minus 1 by t square, and 1 is a constant, so this will be 0. So this is your result. Now let us simplify this result to some extent. You can see here this h nu times this h nu, that will be h square nu square. So let us simplify this result to some extent. So you can see this Cv will be equal to what? This is 3Na, see here 3Na, and h nu times h nu, that will be h square nu square. And see here, this minus 1 and this minus sign, this minus minus will become plus. So this is 3Na h square nu square over see here kt square over kt square and times, see here, e raised to the power h nu by kt, and when you will take this factor in the denominator, the power minus will become plus. So this will be e raised to the power h nu by kt over e raised to the power h nu by kt minus 1 whole square. Now let us arrange the terms in RHS in a particular manner. You can see here this can be written as 3Na times k. Although there is this k is not present in numerator, but I have written it here. So we must divide the expression by this k so that this k will cancel out. So you can write this as 3Na into k times e raised to the power h nu by kt over e raised to the power h nu by kt minus 1 whole square. And see here, the remaining factors are what? H square nu square divided by kt square. But we have written here an extra k in the numerator. So we will also multiply the denominator by this k, and so you can write this will be h nu over kt whole square. So this is expression for Cb, and let us say this is equation number 2. In fact, this expression you can write in a convenient form. By a particular substitution you can see here. So this expression can be written as. In fact, we simply change the form of this equation for convenience. You may write it in this manner: Cv equal to, you know, the product Na times k. What is this? You know, Na into k is equal to what? This is R. This is universal gas constant. You have seen in the earlier lecture. So this may be written as 3R. Na into k is replaced by R. And e raised to the power h nu by kt, we write it e raised to the power theta divided by t. This is capital theta, you can see here, and divided by e raised to the power theta divided by t minus 1 whole square times theta divided by t whole square. We have written this equation number 2 in this form. You can easily recognize what is this capital theta. You can see here that this capital theta is nothing. This has been written at the place of h nu divided by k. You can check it. H nu divided by k. Actually, the value of this nu giving a good fit for a particular solid is represented by a particular symbol nu e, not nu but nu e, because this is just Einstein's formula. So in a convenient manner, we denote this nu by nu e, and we call it simply the Einstein's frequency. Einstein's frequency. And in that case, this capital theta actually corresponds to nu e, and then we will write this theta as theta e. So you can say this nu will be now written by nu e, and this nu e is called Einstein's frequency. Einstein's frequency. This is just a change in symbol. And then this theta, which will be equal to h nu e over k, that will be now written as theta e. And this theta e is known as Einstein's temperature. This is Einstein's temperature. So in this notation, this equation 3 can be written. Particularly with this notation, we will simply change this theta by theta e, and only theta by theta e, as you can see here, and nu is not present, so you can change this formula in this term. This is only to specify that this particular frequency is known as Einstein's frequency, and this h nu e by k is a particular temperature for a given solid, which is called Einstein's temperature. So you can see, so equation, what is the equation number 3? So equation 3 is then written as what we will now write, Cv equal to, you can see this is 3r times this much. So let us write this factor first. So this will be theta e over t whole square times e raised to the power theta e over t and divided by e raised to the power theta e by t minus 1 whole square. Actually, this is our final result, or you can say this is the famous formula for a specific heat of solid proposed or obtained from the Einstein's theory. Or you can also say this is actually Einstein's equation for the specific heat of solid, or you can also say the atomic heat of solid at constant volume. Actually, this equation represents that the specific heat is a function of temperature. You can see in the RHS this temperature T is present, so it is obvious from this equation that a specific heat of solid is not independent of temperature as predicted in classical theory, but actually this specific heat is temperature dependent. And this was actually the aim of Einstein theory, that as experiment says that Cv depends on temperature, so Einstein tried to obtain the expression of a specific heat in such a manner that can explain the temperature dependence of the specific heat of solid. In fact, you can see here this Cv is a function of temperature, and this equation A is Einstein's Einstein's equation for a specific heat of solid. And as I have told you that this equation implies that the specific heat of solid depends on temperature. Actually, now we will discuss in the second lecture the temperature dependence of this specific heat, particularly when temperature is high and particularly when it is low. So in high temperature region and in low temperature region, how the specific heat capacity of temperature of a solid depends on temperature, we will see it. And you will see in the next lecture that at high temperature this formula will simply change to 3R. It means Cv will be equal to 3R, particularly at high temperature, which will agree with the classical result. But I am not going to discuss that in this lecture. In fact, in the next lecture we will see how this Cv varies with temperature, particularly when temperature is very high and when it is very low, because this high and low temperature dependence of Cv is very important for various examinations like civil services examination, even your university examination and other competitive examinations.